Hi class, Dr. Searcy here with the video lecture for the textbook chapter 17. And as you can see, the title of this chapter is the chi-square statistic, tests for goodness of fit and independence. Okay, so to begin, let me just kind of review the idea that all semester long, as we've been talking about the inferential tests, one way that we can refer to them is as parametric tests. Okay, so what is a parametric test? A parametric test is all of the inferential tests that we have gone over so far, right? So that includes measures like Z, the t-score, that f-score where we were calculating the ANOVA, R where we were calculating that Pearson correlation, and then y-hat, which we use to calculate linear regression. Now, we've been able to use all these tests because the data that we've been using with them has always been assumed to fit these three assumptions. And I want to go over what these three assumptions are, right? So now we're talking about the data that we use to calculate these scores. One thing that we can assume about the data is that the means pile up around mu, right? So this is going back to earlier around maybe like chapter 3 or 4, we were saying that we want to make some comment about a population, but we don't have access to everybody in the population, so we pull out samples or sample scores from the population, right? And we pile them in here. So when we're saying that the means pile up around mu, we're saying the means of the sample scores pile up around where the mu score is. Okay, so a second assumption has always been that when we create a new distribution, it's always going to be normally distributed, right? It's going to have that smooth curve. And then a third assumption is that when we're working with data, we're always working with scores that are numbers. And that's how we're able to do the mathematical statistical equations. However, in truth, when we get out in the world and we actually try to analyze data, sometimes what happens is that the data will not fit one of these assumptions. And so when that's the case, we have to not use a parametric test, but find some kind of non-parametric test instead, right? So these are tests that are used when inferential tests used. These are a type of inferential test used when at least one assumption is not met, right? So when you have some data that is either not normally distributed, the data didn't pile up around the mean, or you're not dealing with scores, they're numbers. Then in those situations, you would want to find some type of non-parametric alternative to the parametric test that you wanted to use. One such test is the chi-square test. We can define this test as doing this. It determines whether there is a significant difference between expected and actual frequencies, right? So we should kind of define what we mean by expected and actual frequencies. Actual frequencies, remember frequencies was another term we used earlier in the summer. It's basically how much of something is occurring. So there are two types of that, two types of frequencies. One where there's what actually happened, right? How much of something actually occurred. And the other one is, well, how much did you expect that you were going to get some specific number? Or what did you expect the count to be? Right, so then what we're looking at is the difference between what actually happened and what you expected to happen. When we do this, we like to get data and fit it into different categories and then see how many scores we end up seeing in each category. Now, when we go to run or calculate a chi-square test, there are basically two parts to it. One part is the goodness of fit test. And here we're seeing first that there is a formula associated with this. We start off with this symbol here. This is the symbol that represents chi-square. As it turns out, This is another Greek letter that you're being exposed to, right? The letter chi, and it's squared. So how do we obtain that score? We find the sum of this division this division problem, where FO is, is the observed frequency for a category, right? So that's FO. And FE is the expected frequency for a category. From here, what we need to do is think about what data do we have once we've, what information do we have once we've collected our data? The information that we have is, we know this, right? That's the actual data itself. What we do not necessarily know is the expected frequency. We don't really know what to expect beforehand. So in the equation, the only value that we really have are the FO scores, how often something actually happened. Therefore, we need to have a way of figuring out, well, what is FE? What was that frequent expectancy? Or the expected frequency. So to do that, another thing I should say is that once you've calculated this equation, you're going to get some value for chi-square. And if you have a value that's a large chi-square, that means that you have a significant difference between your actual outcome and your expected outcome. And another way we want to think about this is, if we're thinking about getting some value and looking at whether it's large or not, then we're probably going to want to compare it to some other value to see if it gets above that other value. And the way that we go and find it is, again, we use degrees of freedom. In this case, degrees of freedom at least starts off with knowing what our number of categories are and then subtracting 1 from that. Kind of like the same thing as the ANOVA tests, right? With the ANOVA, we were looking at the number of treatments, and that was represented with that K. Same idea here. Categories are like treatments. Okay, so earlier I was saying that as far as the equation is concerned, we know the FO scores because those are the actual things that happened. We do not necessarily know the FE scores. We do not necessarily know what was expected to happen. So to help us figure that out, we also have a test for independence. This test for independence goes like this. It's another formula, but this time the formula is to solve that FE variable, right? The one that we did not know up here. How does the formula work? Well, FE is going to equal FC times FR divided by N. So now I probably ought to do some more explaining. What are FC and what are FR? FC is the total column frequency, and FR is the total row frequency. And then, of course, you know that N is the sample size. Looks like I trusted so well that you knew that I didn't even write it down. But I'll go ahead and do that just to make sure. Right? Our lowercase n is sample size. Okay. Now, when we actually go to do our analysis, where we compare the large chi-square to some critical value, the degrees of freedom value that we're actually going to use is this one here, where we're saying it's going to be R minus 1, or the number of rows minus 1, times C minus 1, which would be the number of columns minus 1. Right? So multiply those two together, and then you can go look up a critical value on a chi-square table. And we'll talk about that when we get to that step. For right now, though, I want to go over a example problem with you on this. See how it works. So in this example problem, question is being asked, is there a relationship between age and watch preference? Kind of a strange question, right? But we at least see that we're looking to see if something's related. What is it that we're related? We're looking to see if it's related, how old someone is, and what kind of watch they prefer to wear, right? We're looking to see, does age influence that or have a relationship to that? Okay, so hopefully you've heard that it sounds like we're doing a hypothesis test here. And so, yes, if you did hear that, you were correct in thinking that. So we'll go ahead and start the hypothesis test with statement one, or step one, where we calculate, or we talk about our hypothesis. And here, I'll just kind of lay out the whole thing. We're saying that in this example, we have 200 people who we went and asked. Our null hypothesis is that preference is independent of age, right? So there is no relationship between how old someone is and what watch they prefer. However, the alternative hypothesis is exactly the opposite. It's saying that age is related to preference. And we're setting our alpha level at 0.05. So in the chi-square analysis, you would go and you'd set up your data like this, right? First thing that we see is we have 3 categories of preference. We have whether people like to wear a digital watch, right? So that's the ones with just the numbers on it that blink. An analog watch. I believe that's the one with the hands. And then we have a category here of people who have no preference, right? They don't have a decided preference between what kind of watch they prefer to wear. But then over here, we have our 2 categories of age. We've got data representing people who were less than 30, and then we have people who are 30 or above. And for each category, we have numbers that represent them, right? So for instance, this 90 here represents this idea that out of the 200 people surveyed, there were 90 people less than 30 that preferred to wear a digital watch. 40 people less than 30 that wanted the analog, and then 10 that were undecided. Same thing with this row. Here we're saying that we have 10 people, 30 or over, that prefer the digital watch, 40 people, 30 or over, that prefer the analog watch, and then 10 people, 30 or over, that were undecided. One thing that you may notice is that one thing I had to do to my matrix here was I had to take sums of the different values, right? So this 140, that is the sum of this top row. 60 is the sum of the bottom row. And the 100 is the sum of the first column. 80 is the sum of the second column. And 20 is the sum of the third column. Okay, so looks like we have all the information that we needed for step 1. Now we can go ahead and move on to step 2, which is where we're going to locate the critical region. We said that our alpha level was 0.05. Our degrees of freedom formula is C minus 1 times R minus 1. As far as C is concerned, there are 3 columns. As far as R is concerned, there are 2 rows. So our formula ends up being 3 minus 1 times 2 minus 1, which equals 2 minus 1. So we get 2 as the number that we're going to look up. And in terms of our degrees of freedom, by the way, when you go to do this, you're going to go look this up at a chi-square table in your book. It's on page 659. But the table works pretty much the same way that it's been working all semester long. Now it's just for chi-square. At the top, you have the different significant level values, right? The different critical regions. And then on the side to the left, you have different degrees of freedom. We said our degrees of freedom were 2 at 0.05. So that's going to give us a critical value of 5.99. Okay. So from here, we can now move on to the third step of this statistical test. The third step now is where we're doing the calculations. Right, and the first calculation that we need to do is we need to figure out what FE is. But a thing that you want to think about with this is your FE is actually going to be, you're going to have a different FE for the different combinations. And I'll show you how that's going to work. Right, so remember, to find the value for FE, the equation is the frequency in the column times the frequency in the row divided by your overall N. As it turns out, we have to do this for each one of our cells that we have here, right? The cell is a box. So we'll do it for our first cell in the top corner, our less than 30 group who prefer the digital watch. What was their expected frequency? Well, the formula says to take the sum or the frequency of C, and the frequency of C is 100, multiply it by the frequency of R, which is 140, and divide that by the N, which is 200. Turns into a division problem that gives us 70. Right, so now we have an FE score for that category. Just so you see, we're actually going to do an FE score for every single category that we have, for every single cell we have, right? We have 1, 2, 3, 4, 5, 6 different cells. So we're going to end up with 1, 2, 3, 4, 5, 6 different FE scores. And I'll just kind of run them down really quick, right? So for the less than 30 analog, that's this group here. Their FC, right, their column frequency is 80. Their FR, their row frequency is 140 over the N, so that gives us 56. And I'll just kind of run through all the numbers with you on this now. So we have the under 30 undecided. Their frequency for the column was 20, and their frequency for the row was at 140 over the 200, so it gives us an FE score of 14. Now we have to do the same thing for the bottom row here, the 30 or overs. This is the score for the digital cell. Notice that their column frequency was 100 and their row frequency was 60. So that's 100 times 60 over 200 gives us 30. For the analog group, it was 80 times 60 over the 200 gives you 24. For the undecided group, it is 20 times 60 over the 200, which gives you 6. Okay, so now at this point, you are seeing that we've just completed the FE equation, and we needed to complete it so that we could use that information in our chi-squared equation, right? Because we needed to know the FE score here and here. Once we've done that, now what we need to do is organize all the data into a table that will allow us to see how we can do this computation. And so the way that I've organized the table is like this, right? So we're going to have values that are going to go down each column. At the end of the day, the equation that we're going to do is this FO minus FE divided by E. FO minus FE squared divided by FE. That's this here. So then the table is just helping us collect all that information for all the 6 different cells. Okay, so to begin with, let's just take a look at what we got here. Each row is information about one of the cells, right? Say, for instance, this less than 30 digital group, they have that score of 90. That's their observed score, right? So that's going to be the column here. All the FOs, the actual observed scores are going to go here. Here we got 90, 40, 10, 10, 40, 10. That's your 90, 40, 10, 10, 40, 10 right there, right? So those are the observed scores, the scores that you actually got. The FE column is that collection of scores that you just calculated, right? So 70, 56, 14, 30, 24, 6. That's what you got here, 70, 56, 14, 30, 24, 6. Now that we've got all our data together, we can start to do our calculations to find whether we have significance or not. First thing that we need to do is find this difference, so that deviation score between the observed scores and the expected scores. We're doing that for each row that we have. After that, we're going to square each of those individual values, right? So our 20 becomes 400. Our negative 16 becomes 256. And then, once we've done all that, for each row, we are now going to do the calculation, right? So this 5.71 is the result of the calculation. I didn't actually write it down because I thought it was going to be a lot more work than was necessary. But here is the result of each calculation. From here, we're saying that we're still in step 3, right? So we're still doing our calculations. But now we are at the last part of step 3. The last part is you now have to add the last column to get the chi-square, right? So add all of this up, just like the formula said. To get chi-square, you're going to add up all of those different division problems that you had calculated. What's the sum? Well, dun, dun, dun. It ends up being 38.09. Now remember, the critical value that we obtained was 5.99. So what does that mean? Since we have a score of 38.09, we now are able to make our decision. And what is the decision? The decision is that chi-square is in the critical region, right? It's greater than our critical value of the 5.99. So we're going to reject the null. And maybe the last thing that we can add here is how we would state this in terms of like a research report. We would say that there is a relationship between watch preference, right? Whether the person preferred the digital, the analog, or the undecided. There's a difference between that and H. And so then the way that we write it here is we are saying that we got that via chi-square with degrees of freedom of 2, an n of 200, and this was the actual chi-square result, and this was the level of significance that we set. Okay, so that's everything I've got for the lecture on this chapter. Thank you very much.